So today I would like to cover the last section of chapter 7 and then go to chapter 8.
Sorry. Yes, we are going to do chapter 7.5 and the chapter 8, the first two sections of chapter 8. Okay, and we scheduled presentations, and I did not hear from any other requests for the students who haven't been scheduled yet. So if you have any schedule conflict and your presentation has not been scheduled yet, then just let me know your schedule, and I will send you the schedule, the final schedule tonight. Any questions from previous class or any final projects, quizzes? Okay, so I will share the screen for chapter 7. Oh. Yeah, so far we have studied ANOVA, the one-way ANOVA and two-way ANOVA. So that is for the factor predictors. So predictors are factor variables. So the simplest case is to compare two groups. So group 1 and group 2. So that is done by t-test. But if we have more than two groups and we want to see the overall difference between groups, then we can use one-way ANOVA. And if we have the two factors, for example, the yield of crops is determined by the fertilizer and maybe the type of vegetables, then we have the two factors, the vegetables and the fertilizer. Maybe we have 3 fertilizers and 4 vegetables. Then we want to see the overall difference between fertilizers and overall difference between the vegetables. And today's topic, in the last section of 7.5 is using this ANOVA function and the ANOVA method for a regression model. So basically, ANOVA is developed for factor variables, but it can be used for continuous predictors as well. So ANOVA table can be also used to test the significance of predictors in a simple linear regression model. And if we consider the one-way ANOVA with only 2 levels, so that means that our predictor is basically indicator variable for the second group. So say the first group is the baseline, and we have indicator variable of second group. If we have 4 observations and the second and third observations are in group 2, then basically this predictor is used in one-way ANOVA. So in this case, we only have one predictor. And this is similar situation to the linear regression, simple linear regression, y is equal to alpha plus beta times x plus epsilon. Because x is a continuous variable, and so the vector looks different. Maybe x values are 1.1 and 2.3 and 3.5 and maybe 0.9 or something like that. So it looks different, but still it's just one vector. So we have the same structure. So using so the ANOVA can be used to test the significance of the predictor x. So in ANOVA, basically we have important quantity, sum of squared residuals, SSD, and that is defined by yi minus y bar. So this is just one-way ANOVA, and summation I is equal to 1 to n. But we can, sorry, there maybe we have ice group. So maybe I should say that the yi, sorry, maybe, sorry. I would say that if we have index I for group and J is the index for observations within groups, then we calculate this quantity in one-way ANOVA. But for regression model, this is just factor one-way ANOVA. One-way ANOVA, we define sum of squared deviations as this, but for regression, we can just use this as yi. Maybe, yeah, we just have one index here, but maybe I use maybe k, the yk minus the y hat of k. Then we can use it in a similar way. In one-way ANOVA, we have the structure. We have observations within each group, so we use the indices I and j. But for regression model, just we don't have any groups, so I wrote the sum of squared deviation as summation of yk minus y hat k. But the point is, yeah, in ANOVA, we can use the group mean here, and in regression model, that we can use the fitted value here. So we can apply the analysis of variance in a similar way as ANOVA for regression model. So here's an example. We have variable x and variable y, and we do simple linear regression, so y over x. Then we get the intercept and x. These are estimates, and these are t-values, and these are p-values. And yeah, this p-value result indicates that the x has p-value of 0.0640. So this is based on the t-distribution. Okay, so this is usual ANOVA result, usual linear regression result. So basically, if we consider y is equal to, we consider the model y is equal to a plus bx plus epsilon, then this significance of b is decided by this. So if our null hypothesis is b is equal to 0, then t statistic is negative 2.87. So we reject this null hypothesis with this p-value. So if significance level is 0.05, p-value is slightly larger than that. So we do not reject the null hypothesis of b is equal to 0. And this can be done by ANOVA as well. If we make the ANOVA of this linear regression, so this returns this table, and the significance of x is reported as this p-value, which is the same as the previous slide. So we have f value. So this is slightly different from the previous page in terms of expression. But remember that if we have degrees of freedom 1 and 3, so this statistic follows f distribution with degrees of freedom 1 and 3. 1 is for numerator and 3 is for denominator. And actually, this is the square of t distribution with df3. So actually, this is just the squared number of the previous t statistic. In a previous page, the t statistic is negative 2.87. If we square this, then that becomes 8.237. So it's the same as this. Maybe we have some rounding errors, but here. Yeah, so basically we do the same thing. So if the same thing, then we don't really have to use the ANOVA function. So, but that's just the first thing that is that I want you to understand that basically the ANOVA can test the same thing as t-test as well. And also in chapter 11, that we introduce more than one predictor is in linear regression. So we are testing y is equal to a against y is equal to a plus bx1 plus error. Maybe error is always here. And also another model is y is equal to a plus b times x1 plus b maybe b1 x1 plus b2 x2 plus epsilon. So if we compare these models sequentially, we actually need ANOVA table for regression case. We will study it in later. but the ANOVA is sequential test. So if we have more than 2 predictors in regression model, the ANOVA function may be useful. Yes, yeah, but anyway, so we have not studied the multiple linear regression, which have multiple predictors. So we discuss it in chapter 11. I got one question. Oh yeah, actually not a question, just a comment. Yeah. Okay, so do you have any other questions? Okay, so next we go to chapter 8. So just a moment. So chapter 8 is completely different topic than other chapters such as 6, 7, and 11, 13, 12. So chapter 8 deals with the tabular data. So basically, we only have factor variables. So, in statistical analysis, important thing is how, response and predictor looks like. So suppose we have, okay, so predictor and the response. And we studied linear regression in chapter 8. And predictor is continuous and the response is continuous. So this is regression. So chapter 6. If we have multiple variables, we study multiple linear regression in chapter 11. And if predictor is factor, categorical, I would say, categorical or factor, then response is continuous, then that is chapter 7. Okay, so that is the whole point of difference between chapter 6 and 7. The response is continuous in both cases, but the predictors are different. And chapter 8, so maybe I would say the categorical. And chapter 8, basically we want to consider the 2 categorical variables. Maybe more than 2, but the categorical and the categorical. So in this case, we basically don't have a very convenient the regression type models, but if we have 2 categorical variables, that we use the tabular data methods for tabular data. So if both variables are categorical, basically result is summarized as a table. So for example, what we have, yeah, any type of, for example, the maybe blood type, and maybe the gender or something like that. Then we have the genders and blood types. So we have table. So basically, we are analyzing this table. We have some counts such as maybe, okay, so 30 or 50 or 10 or 100 and the 25, 45, and maybe 15 and 90. So we have to analyze a method to analyze. We have to have a method to analyze the tables. So that is the point for chapter 8. By the way, the other chapters, actually the chapters 12, sorry, chapter 13. Chapter 13 deals with the case that the predictor is continuous and response is categorical. Actually, not really categorical, but just binary. So this is chapter 13. This is called logistic regression, so special type of regression model. So response is categorical, binary. That is often the case. For example, the medical data after some treatment, some patients die and some people don't die. So the response is binary, die or not die. So in such a case, that we can use the logistic regression. Yeah. So basically, these are the models we deal with. And chapter 12 deals with some more advanced models beyond chapter 11. That's the that is kind of some additional topics. So yeah, you can see that this overview to consider the final project. So what kind of methods should you use for your data? Okay, so introduction. So basically, we deal with these kind of problems. So first one, when 105 out of 200 newborn babies are male, is the proportion of the males is, in the long run, significantly different from 50%? Okay, so we want to see if there are more boys than girls, and we have a sample of 200 newborn babies, and we found that 105 are male. So that means 105 over 200. So that is 52.5% are male. So should we conclude that there are more boys than girls among newborn babies in the entire world for the next year? No, it's not clear, right? So yeah, okay, so we have more boys, but we only have 200 observations. So that happened just by chance. So we need some statistical method to justify whether this is significantly larger than 50%. By the way, do you know whether we have more boys or more girls among newborn babies? I think it really
I think slightly more girls.
Sorry?
I think slightly more girls.
Actually, more boys. Yeah. Oh. Yeah, basically boys are weaker than girls, so probably that's the reason why, biological reason that we have more boys among newborn babies. Yeah. But the proportion really depends on the country, maybe and other factors, maybe. In some countries, maybe 51%. So it's really an important research question whether this is equal to 50% or not. And the next question is the 100 out of 500 people in the population. So next question is, if 100 out of 500 people in population A prefer Pepsi, while 150 out of 600 people in the population B prefer, these are the same, they prefer Pepsi over Coke. So is there any significant difference between two proportions in terms of preference? So first example, the 100 out of 500. So this is 20%. And the second one, 150 out of 600, so 25%. So it looks different, but we don't know if the difference is significant or not. Maybe 5% difference is a big number, but we want to justify statistically. So that is another question. Well, I think Jordan turned on the video and also answered the question. So maybe I gave him the one bonus credit. Sorry, I think something is wrong. I have to. Sorry, I'm sharing screen, but it doesn't work well. Okay, I think it worked. And this, and the third question. Third question is, in general, if we have the table of counts, whether we have significant difference between two factors. So this is a table for, I think, the graduate students in some statistics department many years ago. So basically, the professor checked the eye color and hair color. So that is a strange data, but then these are counts. So actually, the most frequent combination is the brown eyes and the brown hair and the brown eyes. But we have some different cases. And we see whether these two factors are related or not. Yeah, actually, the brown hair is the most common across all eye colors, but we may have some pattern. For example, maybe we focus on this group and this group. Maybe we can look at these two groups. And we have more black hair people among brown eyes, but less the black hair people among green eyes. So we may have some pattern between these two factors, eyes and the hair. So we want to generally see whether two factors are related or not. So in the first two questions, actually categories are binary. So we only have the two categories, male or female, or prefer Pepsi or not prefer, and population A or B. But in the last question, we have 3 groups for hair and 4 groups for eyes. Okay, so now we have a question. The first question we want to answer. We want to answer the first question, and is 105 males out of 200 babies significantly different from 50%? So sample proportion is 52.5%, but it does not sound unusual. So here is the simulation result under the assumption that the proportion of male is 50%. So suppose that the random number becomes 1 with probability 50%, then we generate the 200 such numbers. Then count how many of them are 1s. So then we can calculate the realization of 1s out of 200 observations. And we repeat that for, I think, the 100,000 times. 100,000 times. Then this is the result. So since the probability of being 1 is 0.5, this is centered at 0.5, but the result has large variation. So maybe from 0.4 to 0.6. So it's very rare to have 0.35 or 0.65, but sometimes the proportion becomes maybe 0.41 or 0.58. So with this simulation, our observation of 105 over 200 is not really special. So 0.5, so this 0.525 is in this 1, 2, 3, so probably in this bin, right? So it's not very special. So it happens even if proportion of male is 50%. So we want to justify this procedure statistically. So our conclusion should be 105 over 200 can happen under the hypothesis of 50% male, 50% female. So we do not reject p is equal to 0.5. We want to justify this procedure statistically. So suppose that we have 200 babies and calculate the proportion of males. So we say that number as p hat, estimate for the proportion of male. And the p hat is approximately normal by central limit theorem. So if you take the 5700, then we have studied p hat is approximately normal. So even 20 to 10 or 5800 discusses that. And since p hat is approximately normal, if we subtract the mean of p hat and divide it by standard error of p hat, that becomes approximately normal 0-1 distribution. So as long as we know expectation of p hat and the variance of p hat, then we can construct this as test statistic. We call it as Z because it follows standard normal distribution. And so we need the formula for expectation of p hat and variance of p hat. So since the true probability is p, we can almost easily see that this is equal to p. What is variance of p hat? I think the stat 20 to 10 as well as maybe 5700 discusses that, but yeah, we just review that. So suppose the true probability of male is p naught because we want to emphasize that is the true value. So p sub 0, p sub p naught. Then if we have one observation, one baby, then what's the expected number of babies? The expected number of babies X. So that is baby is female with probability 1 minus p naught and male with probability p naught. So if we calculate expectation is the probability of xi times probability of xi times xi and take summation over all possible i's. So if we calculate expectation, so that becomes p naught. And what is the variance of x? Then the variance of x is basically the summation of probability of xi times xi minus expectation of xi, right? And expectation of xi is p naught, so I plug in p naught, just blue ones. Then the probability of 0, so xi is equal to 0 is 1 minus p naught and 1 with probability p naught. So if we calculate this variance, this becomes p naught times 1 minus p naught. So p naught is a probability. So if 0.5, then this variance is 0.25. So in general, if we have n babies, we can calculate it in the same way. So p hat estimate of proportion of male is realization of this indicator. The proportion of male is calculated by summation of xi's over n. Here, n is the number of sample size, and each xi is equal to 0 if female and 1 if male. So we can calculate p hat as this. And here, the 0 is with probability 1 minus p naught and 1 with probability p naught with probability. So in this case, expectation of the p hat is calculated by this. So expectation is a linear function. So the expectation of entire quantity is actually this expectation of this quantity, but we can pull out 1 over n before taking expectation, and then we have this. And expectation of summation of xi's is summation of expectation of xi's. So we can decompose this part. So we can get this as p naught. So variance of p hat, slightly more complicated. We want to calculate variance of this p hat. And the variance is at first has property that the variance of a times x is equal to a squared times variance of x. So if we see the definition of variance, always we square the quantity, so everything is squared. So if variance of a is x, then everything every part of the calculation, we square this ax. So we have a square times variance of x. So yeah, and then we get this is equal to 1 over n square times variance of x1 plus x2 plus up to xn. But if x1 to xn are independent, that is basically our assumption. So the newborn baby is male with 50, the probability p0, but the observations are all independent. So the gender of the first baby, it does not affect the gender of the second baby. That is our assumption. And if x1 to xn are independent, the variance also decomposes. So that proof is needs little more algebra, but that is a fact. And so that we can calculate this. And x1 to xn are all binary random variable, either 0 or 1, with probability p0 with the equal to 1 with probability p0. So the everything is the same as just the variance of x in the previous page. So we have n times p0 times 1 minus p0. And 1n cancels with this denominator. So we get this. So this is variance. So finally, the standard error is the square root of variance. So if we subtract mean from p hat and divide this by standard error of p hat, that is standardized. So that becomes mean 0 and the variance 1. So this quantity is approximately follows the normal 0, 1. Yeah, so we can reject the null hypothesis if this z falls in extreme range. So under null hypothesis of male has probability p0, we have this distribution. So this is the distribution of z, so density of z. So distribution of z. So if this falls in extreme, our statistic falls in the extreme range of this distribution, that we reject null hypothesis. So we reject null hypothesis against the p is not equal to p0 if the z falls in this, the extreme range, is the left tail or right tail. If the alternative hypothesis is one-sided, for example, the probability of male is more than 50%, then we only reject h0 if z is large enough. So in such a case, we reject basically if the the z statistic falls in this range. So the right 5%. So for this one, that we throw away probability of alpha over 2 on both sides. But one-sided test, that we throw away the probability of the tail probability of alpha on the only right-hand side. And the other way around is also possible. If alternative hypothesis is p is less than 0.5, we reject null hypothesis if z is small enough, because small z indicate the small small p0. Yeah, so the concrete procedure is here. So in our case, we have 105 males out of 200 babies. So our p hat is 0.525, and we want to test if the true proportion is 0.5. So under this null hypothesis, the expected value is 0.5, and our realization is 0.525. And the standard error of this estimate is square root of 0.5 times 1 minus 0.5 divided by 200. So we get 0.707. 0.707 is just the typical realization of normal random variable. So you can see that the normal distribution is within negative 1.96 and positive 1.96 with 95% probability. So with 5% significance level, any number between these two values is typical. So we cannot reject null hypothesis. So maybe the true proportion may be 50%, maybe slightly less or more, but we cannot reject the null hypothesis of P is 50%. Any questions? Okay, then next one is the R code for the example. So we have 105 over 200, and we have null hypothesis of 0.5. Then we can use this, the prop.test, the test for proportion for this. Then 105 out of 200, the null hypothesis is the probability is 0.5. Then we get the p-value of 0.525. Actually, this uses slightly different statistic than z. Actually, the square of z is returned. So it's not really 0.707, but that statistic, then we have p-value of 0.5245. So this is larger than 0.05, so we do not reject null hypothesis. This is sample proportion, 105 over 200. Yeah, and yeah, it reports so-called chi-squared value. So that is basically the square of the z value. And actually the z square is 0.9498, so that is larger than 0.405, but this difference is due to continuity correction. So we approximate the distribution of p hat by normal distribution, but the p hat is discrete distribution. So at least we have some errors. So if we do continuity correction, then basically we have the same numbers. I got one question. So is there a test without continuity correction? Oh, that's a good question. Yeah, I believe that we have some options in the function. So you can see the help of ROP function. Maybe you have some option. We have correct option. So we can set the correct continuity correction. So correct option is equal to false, then you do not do continuity correction. So you will get the z square, so 0.498. Sometimes packages do some more corrections. So I don't know if it's exactly the same as this, but yeah, at least if you specify option correct is equal to false in prop.test function, then you get closer, well, the same answer as the 0.498. Yeah, that's a good question. Yeah, so the continuity correction is basically adjust the something of the distribution of p hat and z. So anyway, p hat is the discrete, so we cannot fully correct the correction maybe, but still we can do somewhat better than doing nothing. Yeah, and R can also test p hat based on the exact discrete distribution of p hat under null hypothesis. That is in the next page. That is the binom.test function. So we do not use normal approximation. So that means the more computer intensive, more computationally intensive, but this is more accurate. And the more accurate p-value is actually here, the 0.5246. That's very close to the previous page. previous page, that is 0.5245. So it's slightly different, but almost the same answer. So that basically calculates the exact distribution of p hat based on null hypothesis of p is equal to 0.5. Then we have 200 observations. So we have exact, bins. So this bin is for example, the p hat is equal to exactly 100 over 200. So that is 0.50. And the next bin is exactly equal to 101 over 200. So that is 0.5005. No, 505. And 510, and so on. So we do this. And if we make this distribution, we have 200 bins. And approximately normal. And if we fully calculate this distribution, it's more accurate than normal distribution. So the point of normal approximation is to make calculation much faster and easier. So this can be done by binomial test. If these numbers are too large, probably we don't have much benefit, and also it takes too much time. So binom.test is for small observations only. If large, it takes too much time, we have almost no benefit. Yeah, so this sample code, the second sample code is more accurate than one. But two results are very close if the sample size is large. I got another question. So doesn't binom.test also include the continuity correction or not? So binom.test is not using continuous variable. So they calculate exact probability. So we don't have any approximation. Yeah, that's good. Yeah, maybe I will give some bonus credit if you ask a good question, or you turn on video maybe. In dear. I will prepare a new column so it becomes the same scale as the quiz questions. So I will give 1 point for Jordan and Bindia. Okay. Yeah. And the next topic is the confidence interval. So once we got the number, usually we want to get the band. So p hat is, in our case, the 0.525, 105 over 200. So 0.525. But so how accurate this estimate is? So certainly if we get this as 52500, so these numbers are nothing, because anyway, we only have 200 observations. So the fourth place or fifth place doesn't make any sense. That's probably easy to see. But how reliable these numbers, this number is, this 5 really makes sense, or it's not that accurate. And we can say, we can claim that the p hat plus minus this quantile, 1.96, if alpha is 5%, times standard error of p hat as 95% confidence interval. So this interval includes the true p with 95% probability, or in general, 1 minus alpha times 100 probability. Yeah, and the p hat, the z is So the quantile point is 1.96 if 95% confidence interval, and the standard error of p hat is given by this. And some people prefer more conservative methods, and they replace the last factor as square root of 0.5 square times n. So this is slightly larger than this, the p hat times 1 minus p hat over n square root. Because this is the maximum value for this quantity. So p times 1 minus p is maximized at p is equal to 0.5. You can see that if we have p here and we have a function of p, that is y is equal to p times 1 minus p, that is maximized at 0.5. So just to be conservative, that we have larger standard error here. And that isn't really much different from this, but slightly larger. So then we are more assured that this confidence interval covers 95% of the time. So suppose that the p hat is equal to 0.3, for example. Then still, the p hat times 1 minus p hat is equal to 0.3 times 0.7, 0.21. It's not much different from this 0.25, right? And also we take square root, so the difference becomes even smaller. So even if we use the 0.5, it doesn't make it much larger. And also we have guarantee that any p hat is fine with this confidence interval. So to be conservative, some people use the 0.5 square over n, then square root. Yeah, so in our question, okay, so we use the p hat here. Then the p hat plus minus z sub 0.995. So we are calculating 99% confidence interval. Then that is 0.525 plus minus 2.576 times this quantity. This is 0.0353. So we got this. So our point estimate is 52.5%, but we are also 99% confident that the true p is between 43.4% and 61.6%. So that means probably this 2 or this 5 doesn't really matter. So we can just, roughly speaking, we can just say that it's between around 43% to 62%. So the range is pretty wide. So this is somewhat counterintuitive because we have as many as 200 observations. So usually in such a case, we believe that proportion is maybe 52% or 53%, but not really 45% or 60%. But remember that this is the result of just 200 binary numbers, so 1 or 0. So even though we have 200 numbers, each number is either 1 or 0. Just one bit of information. So that is very small amount of information. So even if we have 200 observations, the information, we have not really much information. So it's different from the observed 200 numbers, the continuous numbers. So if we got, for example, 200 observations of the height data of Wayne State University students, those 200 numbers are all continuous numbers, and the one observation has more information. So if you calculate the confidence interval for the average height of Wayne State University students, probably that is within very small range, like the 160 centimeter to 170, maybe even closer, 165 centimeter to 169 centimeter or something like that. So binary observations, each observation has a very small amount of information. Any questions? Okay, so based on survey, more people prefer to discuss the examples by me rather than having exercise session. So yeah, so I will share the screen and I will discuss this example. Sorry, I have. Yeah, I think you are seeing the screen and our screen. And yeah, I think I have to open the slides at first. So the example, exercise example here. Yeah, so the 2000 presidential election in Florida is famous because we have very small margin between the George Bush and the Al Gore. And the number of votes for Bush is the 2,912,790. And the Al Gore got 2,912,253. So the margin is only 537. And also the counting of the votes are really inefficient in Florida, state of Florida. So actually this makes some controversy. So we want to test if this significance is, sorry, I would like to test if this significance is, this difference is significant or not. So the R language we have here. Okay, so we want to use I think this has very large number, so we have to use the prop.test procedure. So at first, we have two numbers, so sample size here. So maybe we calculate the percentage for Bush. At first, the sample proportion. Sample proportion is 50.0046%. And prop.test, the two, yeah, these numbers. And the null hypothesis is p is equal to 0.5. So we got this. So the p-value is 0.82. So it does not reject null hypothesis that the true probability is 50%. So we cannot reject the hypothesis that the Floridans are just, Floridans just voted randomly for two candidates, kind of. Yeah, but anyway, so election is not, statistics. So if one person get more votes, then he or she would be elected. Okay. And the next question. So next section. So now that we are comparing the two proportions, the P1 hat and the P2 hat. So P1 hat is the 100 out of 500. So this isn't really the fraction, but the actual survey. And we have 100 out of 500 people that prefer Pepsi over Coke. And in population 2, 150 out of 600 answered they prefer Pepsi over Coke. Then we want to see the difference between the two. So it's similar question to the previous question, right? So the proportion of male is equal to a certain number or not. But the difference is that actually the two numbers have variabilities in this case. So in the previous one, 0.525 is our proportion, but the 0.5 is a fixed number. But here, P1 hat and P2 hat are both random numbers, so the situation is different. I got one question. So, oh, sorry, you cannot see screen, sorry, yeah. Yeah, so we are P1 hat and P2 hat, and we want to compare this. And this is similar to the previous section. Previous section, we compared the P hat with 0.5, but the 0.5 is a fixed number. But here, both P1 hat and P2 hats have some variability. But still, the normal distribution has good properties so that we can use normal approximation to see the difference between P1 and P2. So P1 hat and P2 hat are both approximately normal, and the two are independent. So our assumption is that the population 1 and the population 2, we randomly selected 500 people and 600 people, and these people are irrelevant. So these are just independent samples. And if these two are independent, then difference between two random variables is still normal. So normal, the linear combination of two independent normal random variables is again normal. So this is again normal. So basically, if we have the expected value and the variance of P1 hat and P2 hat, then we can test the null hypothesis of P1 minus P2 is equal to a certain number. Usually, we want to see if these two proportions are the same or not. So this is 0. In general, we can make it as D. So this is the case. So our null hypothesis is P1 minus P2 is equal to 0. It can be D, but it can be D, but in case of D, the test is more complicated than what we will discuss this page. And P1, H1 is P1 minus P2 is not equal to 0. So we want to test. Then at first, we want to get an estimate for P hat. So estimate of P hat is calculated by the entire the sample proportion of the entire data. So we combined the two population data, so two samples data, so X1 out of N1 and X2 out of N2, and we combine that and calculate P hat. Because we have to calculate the distribution of P1 hat minus P2 hat under null hypothesis. And under null hypothesis, P1 and P2 are the same. So we can use the entire information to estimate one P hat. If this number is D, we cannot do that. So the test is more complicated. But in our case, we can use just both samples to estimate the best, estimate of P. Then, yeah. So then, basically, we can have the same property as the theorem in the previous section. So P1 hat minus P2 hat, the mean of P1 minus P2. And in our case, it's 0. And this denominator is the standard error of P hat. Standard error of, sorry, this is actually the standard error. This is standard error of P1 hat minus P2 hat. So since we know that P1 hat minus P2 hat is approximately normal, this Z follows approximately normal 0, 1. So we can do a similar test as previous section. So that is, we reject null hypothesis if this Z value is larger in absolute value. So we reject the both tails of the distribution. If one-sided, we have a similar thing. So if P1 minus P2 is larger than 0 is the alternative hypothesis, we reject H0 if Z is large enough, because large Z means P1 hat is larger than P2 hat. And the other way around is possible. So we can test alternative hypothesis of P1 minus P2 is less than 0. So what happens in our case? We have two proportions, P1 hat and P2 hat here, and combined the P hat is 0.2273. So P1 hat is 0.2, P2 hat is 0.25. And if we combined, the overall sample proportion is 22.73%. Then we calculate the z-value, p1 hat minus p2 hat, and divide it by p hat times 1 minus p hat times 1 over n1, and this is sample size for sample 1, and the 1 over 600. 600 is the sample size for the second one. Then the z-value is negative 1.97, slightly larger than the threshold. So we reject null hypothesis at 5% significance level. So now we conclude that P1 minus P2 is not equal to 0, or P1 is not equal to P2. And it can be done by prop.test function, the same function as the one sample proportion, but just we have two input, this one and this one. So 100 out of, oh, sorry, the other way around. So 100 out of 500 and 150 out of 600. So in this way. So the proportion 1 is 0.20, proportion 2 is 0.25, and the difference is 0.05768. And actually, in the previous case, we rejected null hypothesis, but in this R output, we cannot reject null hypothesis. It's really, the conclusion is on the boundary. So we have continuity correction. So result becomes slightly different. In the previous page, probably p-value is 0.04 something, 0.045 or something like that. But here, p-value is slightly larger than 0.05. So difference comes from continuity correction. And which one we should choose? Yeah, actually continuity correction makes it slightly more accurate. So probably that we should use this result practically. Yeah, so the R output calculates the test statistic of the 3.60, and our calculation, without continuity correction, that is 3.88. Any questions so far? Okay, so the next one is the example. This is from the real data. I think until about 10 years ago, the Wayne State University published the matriculation data for medical school. So we know how many applicants from each undergraduate institution and how many applicants actually enrolled in the medical school. And the U of M, 85 out of 483, and Wayne State, 54 out of 143, and Michigan State, 35 out of 266. And you can see that the proportion is highest among Wayne State University graduates, and the U of M probably second, and the Michigan State third. And just for now, that we want to compare these two universities, U of M and Wayne State. We want to see whether these proportions, 85 over 483 and 54 over 143 is significant or not. So this is about 0.3 something, right? So 3.5 or something. And the first one is about this 0.18 or something. So it's pretty different. So, but the samples are, I don't know, they're somewhat large. So probably that we can say Wayne State University applicants have higher proportion of enrolling in the program. So this is enrollment, so not really the admission. So it does not mean the more percentage is accepted, but at least we can say whether Wayne State University graduates enrolled at a higher percentage. And this is the result. So proportion 85 out of 483 and 54 out of 143. and the proportion is 0.176 and 0.37778 maybe. Then the p-value is very significant. So we can say that the applicants from Wayne State actually enrolled with a higher percentage. Yeah, and also it gives the confidence interval. We haven't discussed the exact formula, but we have confidence interval, 95% confidence interval for the difference between P1 and P2. And the P1 is U of M, and the P2 is Wayne State, and the difference is between negative 0.29 and the negative 0.11. So U of M applicants have 11 to 29% lower enrollment rate compared to Wayne State University graduates. Yeah, so that's the result. Yeah, I think this is the end of 8.2. Yeah. Do you have any questions? Yeah, the 8.3 is a longer section, so maybe I can just show just ideas for 8.3 and 8.4. Yeah. So the next, oh yeah, I got a question from Sakina. What is the relation between chi-squared and the proportion test? Yeah, yeah. So that is again, chi-square value is the squared z value. So this is z square. Yep. Okay, so just maybe the overview of the next section. So in the section 8.3 and 8.4, and the we want to see the last question of this chapter. So that is the whether two factors are related or not. Two factors are independent or not. So suppose we have this kind of table. So this is the height and academic performance of grade 5 pupils, and the academic performance is either good or poor. We have just the binary scale. And also we have information of whether those kids are more than 150 centimeters or less than 150 centimeters. And suppose these are observations in one class. So 10 students are good and more than 150 centimeters, and 8 students are good and less than 150 centimeters, and so on. So in total, we have 30 students. We have 18 good and 12 poor performances, and 20 students more than 150 centimeters, and 10 students less than 150. And yeah, okay, so when we see this, it sounds like the smaller students did better in academic performance. So some people argue that some kids that develop the intellectual skill first, and some kids that grow fast. So, and finally we got the same result, but we have some discrepancy in the middle. So sometimes we have this kind of data. But we want to formally test whether the academic performance and the height are related or not. And here is an idea. So we have this actual table, actual count, but also we calculate the subtotals and also expected frequencies of these 4 cells with assuming the independence of height and academic performance. Sorry, I think yeah. So we calculate, okay, so subtotals, the 20, 10, and 18, and 12, right? And so that means that we have, okay, 18 out of 30. So 60% of students have good academic performance. And here is 20. So 20 out of 30. So the 0.67. So 67% of students are more than 150 centimeters. So actually, if we have 30 observations, we expect, so if these two factors are independent, we expect that the 30 times 0.6 times 0.67. So this many students should be in this cell. So 30 times 0.6 is 18, and 18 times the 0.67, actually 2/3 is 12. So actually this is 12. So if these two factors are independent, we expect that we have 12 students here, and 8 students here, and 6 students here. So you can calculate the 20 and 12, so we can calculate this as 8. But yeah, this is 6 and this is 4. So yeah, so overall, if 60% of students have good academic performance, then in this subgroup, the 60% should be here. In this subgroup, also 60% is here. So this table that should appear. But the actual observation, actual counts are here. So we compare this actual counts with this expected counts. We see the discrepancy between 10 and 12, 8 and 6, and 10 and 8, and 2 and 4. So this is the idea to test the difference, test the independence of these two factors, the height and academic performance. Yeah, I think we don't have the much more time, so that we stop here. And if you don't have questions, then oh yeah, I got one message. When you do the list in the prop.test for 2 different p-hats, does the order you put them in the list affects the result? Oh yeah, that's a good question. So who asked? Oh, Neil. The answer is no, it does not really matter. So if you change the order of this, you get the same answer. Yeah. Okay, so that's basically the 8.1 and 8.2 and the rough idea for 8.3. So next time that we discuss the more details about the 8.3 and 4. Okay, so see you on Thursday.